Good day. My name is Kaidit Phua, and I'm a retired professor of public health. I used to teach at the School of Medicine and Health Sciences, Monash University, Malaysia. The topic of this short lecture is statistical analysis for the mathematically challenged, meaning people who have studied statistics but have a difficulty following it, and but who still wish to use statistics or statistical tests to analyze the data. Now, how do you select an appropriate statistical test to analyze your data? Right? It's actually relatively easy, and it can be done with the help of tables such as presented in the next few slides. Okay, please note that this table has been adapted from table 37.1, selecting a statistical test and presented at this particular website. Okay, if you collected data, first thing you need to do is to determine, right, the top row here, whether your data has been collected from an underlying normal distribution, right? Normal distribution, unimodal, bell-shaped curve, right? Symmetrical, and variables which are normally distributed include things such as height and weight. Okay, has the data been collected from a distribution which is not a normal one, right? So is it skewed in some way? And then the third, your outcome can be binomial, only two possible outcomes. Okay, so then on the left hand side of the table, right, the leftmost column, how many samples have you collected? Have you just collected one sample? Have you collected one sample but you wish to compare it with a hypothetical distribution? Have you collected two samples but they are not paired or matched in any way? Or have you collected two samples but they've been paired or matched? For example, you have a sample of research subjects, right? And you collect data on them before your experimental intervention, and then you collect data on them after the intervention, right? So for example, hypertensive patients at the start of the research, and then at the end of the research, maybe 3 months after they've been placed on hypertension medication, and you want to see if there's any difference in the blood pressure, right? The systolic blood pressure, diastolic blood pressure, etc. Then it would be before, after, and that would be pairing or matching. Okay, have you collected 3 or more samples but they are not matched in any way? Or have you collected 3 or more samples but they've been matched? Okay, so if you have only collected one sample from a normal distribution, right? So you can use descriptive statistics to analyze the data. You can use a measure of central tendency, such as the mean, right? Or you can use a measure of dispersion, how spread out the data is, such as the standard deviation or the variance. Now, if your data has been collected from a distribution which is not a normal distribution, then it's not correct to use the mean, right? But you'll use the median. You calculate the median as the measure of central tendency. And then the measure of dispersion or measure of spread would be something like, such as the interquartile range. Now, if your data is a binomial, two possible outcomes, then you use proportion. Okay, if you have collected a sample and you wish to compare to a hypothetical distribution collected from underlying population which is normally distributed, then you use the student's t-test for one sample. Note, if the sample is greater than 29, then you use the z-test or z-test, right? Data collected from a distribution which is not a normal one, then you use a Wilcoxon's sign rank test. Okay, then for binomial outcomes, right? So you can collect the data and then you can use the chi-square goodness of fit test, right? How well does your data from your one sample fit a hypothetical distribution? Okay, if you have compared two samples, but there hasn't been any pairing or matching, collected from an underlying population which is normally distributed, then use the student's t-test for unpaired samples, right? Student's t-test for unpaired samples. Sample size is greater than 29, use the z-test. Data collected from a population which is not a normal distribution, right? Two samples, unpaired, unmatched, use the Mann-Whitney test or the Wilcoxon rank sums test. The binomial outcomes, right? Use a chi-square test of association, right? If it's a small sample, use Fisher's exact test. Okay, if you have collected two samples and they are paired or matched, underlying population is normal, right? Then use student's t-test for two paired samples, right? Underlying population not normally distributed, use the Wilcoxon match pairs signed rank test. And then outcomes, which are binomial, use the McNemar's test. Now, if you have data from three samples, but they are not matched in any way, underlying population is normally distributed, use the one-way ANOVA, or one-way analysis of variance. Underlying population not normally distributed, use Kruskal-Wallis one-way analysis of variance test. Okay, and then binomial outcomes, use chi-square test of association. You have three samples, they're matched, right? So underlying population is normally distributed, use the repeated measures ANOVA. Underlying population not a normal distribution, use Friedman's two-way analysis of variance test. Binomial outcomes, right? Three or more matched samples, use Cochrane Q test. Sometimes you may want to measure association between two variables, right? So again, underlying normal distribution, use Pearson's correlation coefficient. Calculate Pearson's correlation coefficient, right? Underlying population not a normal distribution, use Spearman's rank correlation coefficient. Binomial outcomes, contingency coefficients. Sometimes you may want to predict the value of one variable from another variable. For example, you want to predict the value of the dependent variable y from independent variable x, right? So use a simple linear regression for underlying populations which are normally distributed. And if underlying population is not normally distributed, use a non-parametric regression, right? Binomial outcomes, only two possible outcomes, yes or no, right? That sort of thing, alive or dead, right? Sick or not sick. Then use simple logistic regression. Sometimes you want to predict the value of the dependent variable y using more than one independent variable, right? So x1, x2, and so on, right? Then normal distribution, use multiple linear regression. And if it's binomial outcomes, use multiple logistic regression. Okay, after choosing a statistical test, right, you input your data, you run the statistical test, and then you get output. So the challenge now is to interpret your output correctly from your statistical test. Here's one website where you can input data, and then you can get your output, right? And then you draw conclusions from your output. Okay, first thing you do after running a statistical test is to look at the p-value. if the p-value is less than 0.05, it is statistically significant. That means something real is going on, and the chances that you have made a mistake by concluding that something real is going on is low, right? It's less than 0.05. You will then reject H0, your null hypothesis, and accept H1, your research hypothesis, or your alternative hypothesis. Now, if the p-value is less than 0.01, even better. It is highly statistically significant. So again, reject H0, accept H1, and your chance of making an error is less than 0.01. So as I mentioned earlier, H0 is the null hypothesis. H1 is the research hypothesis or the alternative hypothesis, right? The null hypothesis is a hypothesis you wish to reject, and it is usually stated in a negative manner. For example, for the chi-square test of association, the null hypothesis is there is no association between variable x and variable y. Any association you see is due to chance, right? And for the t-test of difference between two means, your null hypothesis is there is no difference between population mean and population mean x and population mean y. Sometimes output from a statistical test includes a 95% confidence interval, right? In public health, there's something called relative risk analysis or odds ratio analysis, right? And you enter the data, you calculate the relative risk or the odds ratio, and then the output includes a 95% confidence interval. Okay, here you reject H0 and accept H1 if the 95% confidence interval does not contain 1, right? But for the t-test of difference between two population means, you reject H0 and accept H1 if the 95% confidence interval does not contain 0. Note that here is does not contain 1, here is does not contain 0, right? Does not contain 0 means you are actually quite confident, right? High degree of confidence, right? That if you reject H0 and accept H1, your chance of making a mistake is low, all right? You are 95% confidence, right? Roughly speaking, right? That the real confidence interval does not contain 0. So very high degree of confidence. It's not 0. 0 meaning there's no difference, right? Okay, here are some additional resources to help you understand statistics. Some notes on biostatistics, right? At this link here, right? And here is a textbook, a statistical textbook online, which you can consult too, right? From this company called StatSoft. Here are some useful statistics books. The first two books I have co-authored. This book is by some other author, but I find it well written, right, and easy to follow. Okay, so this textbook I've co-authored with another person, and this one with another former colleague too. This is the end of my short lecture. I hope that is useful to you in your selection of statistical tests, right, and interpretation of the output. Thank you for listening. Bye.